Okay, now we're going to work some problems to get familiar with this idea of impedance. So, exercise 1, here we go. We're going to have a parallel RLC circuit. And we'll call this VG. We'll have 5 ohms. We'll have 2, start over. 5 ohms over here, 2 millifarad, and 0.1 Henry. Now, VG, we're going to say, is some exponentially decaying signal. Now, we haven't dealt with this before, so don't be alarmed. You're not supposed to remember having solved this kind of problem before. You certainly should be familiar with an exponential decay, but that's always been the response that we've seen the circuit have to maybe a DC excitation or so. Well, here we're going to actually excite the circuit with an exponential decay. So what we want to do first is let's redraw, I'll call this redraw for S is equal to, and what is S? Well, we're forcing this at e to the st, right? Where S is equal to minus 1 over 2 milliseconds. Right, so it's 1,000 over 2, that's minus 500. And it will be, actually it's nippers per second. Okay, so S is minus 500. So if we redraw this, we'll have 10 e to the minus 500 t. And then what is our capacitor going to be? Well, let's go ahead and calculate it here. Let's say Z of C of S is equal to 1 over SC, right? Which is equal to 1 over minus 500 times C, which is 2 millifarad. All right, so that's 0.5. This will be 0.5 K times 2, which will be 1. So this will be minus 1, and it's going to be ohms. Right? Remember, impedance has units of ohms. The impedance of the inductor is S times L. So minus 500 times 0.1 Henry. And we'll have, I should write nippers per second. I'm being sloppy here with the units. This will be minus 50 ohms. So we can redraw our circuit with actual impedance values. We could say minus 1 ohm and minus 50 ohms. And then R remains 5 ohms. Now that looks awfully strange, right? I mean, we've never dealt with any kind of negative impedance. Now this is not negative resistance, it's negative impedance. These values are only valid for S is equal to minus 500, right? So consider VG equal to 10. Then we would have S is equal to 0, right? Well, Z of C of S, let's say at S equals 0, is going to be 1 over 0 C, so it's going to be infinity, right? And ZL of S is going to be equal to 0 times L, or 0. So now we can draw our network, or we draw our circuit, I should say, where we have an open, and we have a short, and we have our 5 ohms. Right? And we could have done this, we did this even before we had impedance in our toolbox, but now we have, it confirms our findings from previously. Again, so this is infinite, this is 0. These are only valid for S is equal to 0. Okay, so that's what's different with impedance from resistance. Resistance was valid no matter what you were exciting the circuit with, right? But now we have to be careful. Impedance actually is a function of what you excite the circuit with. If you excite it with S equal minus 500 or S equals 0, you're going to have different impedances. Okay. Now, interestingly, okay, no, we'll stop here. So let's go on to problem 2. Okay, in problem 2, I'm given this RRC network. Okay, this is R1, this is R, and this is C. You have IC flowing here, and the values are 4 ohms, 1/4 farad, I believe, and 2 ohms. Okay, and we have an input voltage V and a current I. And suppose V is equal to 6 e to the minus 2t. Again, this exponential decay. We haven't solved anything with this yet, with this form of excitation, but we have all the tools to do so. So we're going to actually do it right here. Okay. So here's our approach. We want to find, what is it that we want to find? We want to find the current through the capacitor. All right, and here's the voltage across the capacitor. So the approach we want to take is, I want to redraw this where I have a resistance R1, and then I lump these two, the R and the C, together, call it Z, and then I'm going to find the voltage across here as being equal to just Z over Z plus R1 times, I guess I should call this VC, times V, which is over here. Right? I'm going to use the voltage divider. So this is going to be step 1. Right? Then step 2 is going to be, IC is simply equal to VC divided by the impedance of the capacitor. Right? So I'm going to get the voltage first, that's across the capacitor and the resistor R, and then I'm going to calculate the current. So let's find Z. Okay, I'll call it ZRC because it's the parallel combination of the two. Well, it's R in parallel with the impedance of the capacitor, which is 1 over SC. So I get R 1 over SC over R plus 1 over SC. Multiply through by SC, and I'll have R over 1 plus SRC. Okay? Now, we can go ahead and plug some numbers in here. We know that R is equal to 4 ohms. We have S. What is S? Well, we're exciting it with 6 e to the minus 2t. So S is minus 2 due to the 6 e to the minus 2t. All right? So we'll have, minus 2 times 4 times C, which is 1/4. Cross that, I'll just drop the units here for the moment. No, I did, no, that's right. Okay, then we'll have 4 over, looks like we'll have 1 minus 2. So we'll have minus 1. So we have minus 4 ohms for ZRC. So therefore, we can write the capacitor voltage VC. Remember, I'm going to use this voltage divider. It's Z, which is minus 4 ohms, over Z, or ZRC, plus R1. R1 is 2 ohms, times the voltage that I'm exciting this with, which is 6 e to the minus 2t. So what do we have? We have minus 4 over 2, minus 4 over minus 2 times 6 e to the minus 2t. So that means we have 12 e to the minus 2t volts. Now finally, to get IC, we say VC divided by the impedance of the capacitor. Well, what's the impedance of the capacitor? It is 1 over SC. So I'll just write SC times VC. The S is, remember, minus 2, and C is 1/4. And VC is 12 e to the minus 2t. So we have minus 6 e to the minus 2t. So the current that flows through this capacitor starts at, oops, I drew it wrong here, starts at minus 6 and goes to 0, minus 6 amps. Now, let's just give it a thought. Does this make sense? What's going on here is that the input voltage, V, is this exponential decay. So the input voltage is decreasing. It has been much, much higher. All right, and the thing to remember here is that although I drew this as having started at 0, it actually has been going on and on and on from infinity past. Just like we'd say a DC voltage has been going on forever and ever. So it was much, much larger, the input voltage, and now it's much smaller. That means that the capacitor voltage, or evidently, the capacitor voltage must have been greater as well and is now going down, because the solution here is that the capacitor current is negative, meaning that the voltage on the capacitor is decreasing and decreasing exponentially. And that would make sense, since the input is decaying exponentially, and if the capacitor voltage is was at one point charged up and now it's being discharged by virtue of the input voltage V collapsing, then it would make sense that the current is flowing out of the capacitor and back toward the input voltage source V, and obviously through R as well. Let's do one more thing. Let's write. Okay, let's find the impedance ZS. Okay, looking into the network. Okay, I'll just redraw it here. All right. What is that impedance? We have R1, R, and C. Well, ZS is equal to, let's see, R1 is 2 ohms. So it's R1. I'll just write the symbols first. R1 plus R in parallel with 1 over SC. Okay, so we have R1 plus R 1 over SC. Oh, and I already did this piece here. I did that. Let me go ahead and write that. It is R over 1 plus S RC. But now let's put this over a common denominator. So we'll have R1 plus S R R1C plus R is equal to 1 plus S RC. Okay, now we can write, let's do this. I see an R and R1 plus an S R R1C. And what I'm going to do is divide all of this by R plus R1. You'll see in a moment why. And then 1 plus S RC. And I guess I better multiply this back by 1 by R plus R1. Okay. So I get in the numerator 1 plus S R R1 over R1 plus R times C, whole thing over 1 plus S RC, and the whole thing times R plus R1. Now notice that this here is simply the parallel combination. I'll call it RP. It's the parallel combination of R and R1. So I'll write this one last time. S1 plus S times RP for the parallel combination over 1 plus S R. Oops, forgot the C. S times RC. The whole thing times R plus R1. Now if we plug in values, let's plug in values here. We'll have 1 plus The parallel combination of the two resistors, let's calculate that over here. Rp is equal to, it's 2 and 4 ohms, so it's going to be 2 times 4 over 2 plus 4, so it's 2 times 4 over 6, so we'll have 4/3. Okay, so it will be S 4/3 times 1/4 farad over 1 plus S R is 4 times 1/4 times 4 plus 2. Alright, let's simplify that. 1 plus 1/3 S over 1 plus S times 6. Multiply through by 3 here, because I want to get this 1/3 out from the S. So now we'll have S plus 3 over S plus 1 times 2. Alright, there we go. So for this circuit, this is the impedance function. Now, do you recall, let's draw this as a 2-port. And if I asked for what is the, say, find the natural voltage response and find the natural current response, we can do this, right? This would be, the natural voltage response would be when there's nothing connected, right? So therefore it's I is equal to 0, and we're looking for the poles, all right, poles of Z of S. Well, what's the poles? The poles in this case are the S plus 1 is equal to 0, right? So S is equal to minus 1 is a pole. And I use the symbol P for pole. So we might write it like this. See, if I plug in minus 1 right there, then the denominator goes to 0 and Z sub S blows up. Therefore, the natural voltage response, VH, is going to be of the form A e to the minus 1 t. And the natural current response is where I short this, right? And I'll have some current flowing, I. And we'll have V is equal to 0 in this case. So we're looking for the 0 of the impedance. So this is the zeros of Z of S. What are the zeros? That's the numerator. S plus 3 equals 0. So therefore I get S equal minus 3, or Z for 0 is equal to minus 3. And thus the homogeneous current response is equal to A e to the minus 3t. And let's just draw this circuit in both cases. When it's open, I have R1 and R, which has a value of 4, and a capacitor has a value of 1/4. Now look at this. This guy here has no effect at all because the port is open, no current flows. So all I have is a 4 ohm resistor and a 1/4 farad cap. This has a time constant equal to 4 times 1/4 is equal to 1 second. Well, that's exactly what I found here, right? And then in the other case, the second case, I'm actually shorting the input, right? So I have 2 and 4 in parallel. These join 2 and 4 in parallel is equal to 8 over 6, or is that right? Yeah, 8 over 6, or 4/3, right? So therefore I take both of these and I see a time constant of 1/4 times 4/3 is equal to 1/3. All right, 1/3 of a second. And that is exactly what I have here. All right, this is t over tau, so tau is 1/3. Let's do something interesting here with z. Let's plot z of s for real values of s. Okay, so we're going to plot, there we go. Here's s, real values. And what do we know? We know that z of s will be 0 when s is equal to -3. I should have gone over here. -3, -2, -1. And what will it evaluate to? Let's see, so it's 0 here. And then at -1 it actually blows up. Right? If it's a little bit greater than -1, so -1.1, then it's going to be negative. Let me do it this way. It's going to be negative. All right? And if it's a greater than, a little less than -1, it will be a positive. Let's evaluate the function at s equal -2. So we have -2 plus 3. That's 1, divided by -2 plus 1, and that's -1. So we have 1 divided by -1 times 2, -2. So let's say 1, 2, -1, -2. So here I'm at this value here. Is blowing up like this, right? And let's see, if we let s become very negative, let's say that it goes -100, okay? At -100 we have let's just do this over here. If s is equal to let's say 1,000, okay? S equal -1,000, then we have z of -1,000 is equal to 2 times -1,000 plus 3 over -1,000 plus 1, right? Which is going to be approximately 2, right? So asymptotically, this thing is approaching 2. So this is going to go through here, and it's asymptotically going off to be equal to 2. All right. Then on the positive side, let's say that it's equal to 1,000 plus 1,000. Then where does it go? Well, it would do the same thing. Z of plus 1,000 would also be equal to 2. So evidently, this is the asymptotic value there. So I didn't draw this very well. Okay, so it looks like this. And here, it blows up. Okay? So we have a pole at -1, and we have a 0 at -3. And if we're above the pole, then we have positive resist impedance, and if we're below the pole, we have negative impedance. Well, negative impedance out to -3, s -3, and then it becomes positive again. And asymptotically, it arrives back at 2. Now think about this network. If I'm at 0 frequency, then this cap here is an open circuit, right? And the only thing that I would have at 0 would be 2 plus 4 ohms. So although I didn't show it on here, I guess I didn't draw it very well. This right here, didn't draw it to scale. This at 0 should be equal to 6 ohms, right? 2 plus 4 is equal to 6 ohms. All right. Now it turns out, we'll see eventually, that the impedance, or the values of S, can actually be complex, right? They don't need to be purely real. They can be imaginary as well. And we won't spend much time at all trying to graph this impedance function in this manner. It's difficult to plot it on anything but like the real axis or maybe the imaginary axis. But we will not, no worries, we're not going to be doing three-dimensional surfaces or surface plots of impedance versus real S and imaginary S. But still, this gives us some insight. Just plotting ZS versus the real values of S gives us some insight onto this impedance function.